Welcome back to our video lectures on the course Material Science and Metallurgy. In today's topic, we will discuss on the crystal structures of metals. Coordination number, then we have the atomic packing factor. So, if you see the coordination number, as the name implies, the coordination, right? The coordination between the atoms. So, for in that particular crystal structure, for that particular metal, so each atom has the same number of nearest neighbor or touching atoms. Okay, so each atom will have the same number of adjacent or the nearest neighbor atoms or the atoms that are in touch, right? So that number is same, and that number is called as coordination number for every crystal structure, for every metal which is having a crystal structure. In that, so each atom will be having the same number of nearest neighborhood atoms. So that number, how many numbers one particular atom is being coordinating with the adjacent, the immediate adjacent atoms, or the atom that has been coordinating. So that is called as, that number is called as a coordination number. Okay. Then atomic packing factor. Atomic packing factor can be defined as, it is a ratio between the volume of atoms, okay, the volume of atoms occupied in the unit cell to the total unit cell volume. So previously we have seen the way how we have positioned the atoms, right, within the unit cell. So these atoms will not occupy the 100% of the unit cell, right? There will be a minor gaps that is present. So that the packing density or the packing factor, so how much of volume that is being occupied by the atoms in the unit cell, that is divided with the total unit cell volume, and that gives your packing density or atomic packing factor. It is also called as APF in short form, atomic packing factor, and sometimes packing factor alone, and sometimes we can call it as a packing density. So all implies to the same parameter, atomic packing factor, the volume of the atoms occupied in the unit cell to the total unit cell volume. Then the calculation of atomic packing factor, and we look at the coordinate, we will try to find out the coordination number also. We start with one structure in this class, that is a simple cubic structure. We look at the simple cubic structure. So this is our simple cubic structure. In the simple cubic structure, atoms are positioned at the corners of the cube. So there are 8 corners. So these are the 8 atoms that are being situated in the unit cell, right? So first we will try to identify the relation between the lattice constant and the radius of the atom. So radius of the atom is nothing but from this to this distance, and that is the radius, and this is a diameter, right? So this is your radius, and lattice constant is this one, the distance between the one edge length of the unit cell, and that is called as lattice constant. Lattice constant, here we are denoting it as A, and radius of the atom, here we are considering it as R. Okay, if you look at the relationship between the radius of atom, so if you recall previously in the body centered one, so if I can draw here, so this is your unit cell, okay. So if you look at atoms are like this. Okay, similarly this is another atom that has been shared. So this is how we can represent it, right? So this is a one complete atom. So this is your atom, right? Okay, this is another atom. So that is the atom that we have it. So if you look at one rectangular box, if I take it only one square box, one face, if I take it, so how I can this particular face, if I write it down, so this is atom is like this, just to identify the relation, right? So this is the atom, so this is what, this is the radius, this is the radius, and this is your lattice constant, and this is your lattice constant. This is all the lattice constant, right? Since it is a cube, all sides are equal, so lattice constant will remain the same. So this is R, and this is also R, so the total is 2R, right? 2R. So this is nothing but, it's also A, the lattice constant. And so I can write it, the relation between the lattice constant, that is A, that is equal to 2R, that is a radius of atom, right? So similarly, we will calculate the effective number of atoms. So how many total in a unit cell in particular, if you consider how many number of atoms that is present within this unit cell. So if you look at, so each corner is being considered with each corner is positioned with the atom, but this entire atom will not be situated, entire atom is not belongs to this particular unit cell. This atom is shared with the adjacent unit cells also. So this is one of the unit cell. So in a three-dimensional space, just adjacent to this, there will, one more unit cell will be present, right? So here itself, so if I can draw here, so if I take one unit cell here, so immediately next to that another unit cell will be there, another unit cell, let me take it in another color, one more unit cell. So this is similarly one more unit cell will be present. Similarly here also we will be, if you extend the same length, so we have here one more unit cell, right? Similarly on top also you are having one more, right? Right. So just for the simplicity's sake, I'll try to neglect this part. So if you look at, yeah, so this unit cell that is also present, there will be an adjacent unit cell as well. So if I take atom here, so where is my atom? So let me take this blue color, and I have placed it one complete atom at the corner, right? This is an atom. So this is being shared with this unit cell and this particular unit cell, right? So similarly at the front I'll be having two more, 2, 3 and 4, okay, front, just in front of this unit cell I'll be having third and fourth, and similarly on the top I'll be having 2 more, like this. Each atom that is been shared with 8 adjacent unit cells. So 8 adjacent unit cells. Each atom is shared with 8 adjacent unit cells. So how much is the portion? If you look at, if you calculate the portion of atom that can be considered within a unit cell, that is, since one atom is there, so it has been shared with 8. So 1/8 of the portion only it has been coming to one unit cell. That is for the one corner. So how many corners are there? There are 8 corners are there, multiplied by at each corner, so 1/8 of atom is present, right? So 8 multiplied by 1/8, that I can consider it as 1. So what is the effective number of atoms? So in total, if I can sum up, in total, so it is having 1 complete atom. You are getting 1 atom. Okay. Yes, this is your effective number of atoms for simple cube. So then we'll try to calculate the APF, atomic packing factor. So what is the definition of atomic packing factor? So the definition for atomic packing factor is the volume of atoms occupied in a unit cell to the total unit cell volume. So APF, how do I write it? APF that is equal to, I can write it as volume of atoms, that is nothing but the number of atoms. Okay, number of atoms, total how many atoms will be present, that we have to consider, multiplied by the volume of that particular atom. So number of atoms multiplied by volume of atoms, I can write it, the volume of atoms occupied in a unit cell, the total number of atoms, that is the effective number of atoms, multiplied by volume of atom, that is divided by the total unit cell volume. So unit cell is a cube, so that is volume of cube. We know lattice constant is A, right? So now how do I write it? N multiplied by, so volume of atom is considered to be a sphere. The volume of sphere, it is nothing but volume of sphere, that is 4/3 pi r cube. 4/3 pi r cube divided by volume of unit cell. Unit cell is a cube, so lattice constant, that is the edge length, is A, that is nothing but A cube. The volume of the cube is A cube. 4/3 pi r cube, I think it is not visible here, so I am writing it here again. So 4/3 pi r cube divided by A, the relation between A and R, that is a lattice constant, and the radius of atom, that is A, that is equal to 2R. I am substituting A in terms of R cube, so that is nothing but your this thing. So 4/3, how do I write it? 4/3, so 4/3 pi r cube divided by, so I have 2r, so 2 cube is nothing but 8 multiplied by r cube. So I'll change the color and we'll strike it off. So r cube will get cancelled, and 4 2 ja, so that is nothing but, so that is, if you calculate, the value will come as 0.52. So 0.52 is the atomic packing factor, APF, for your simple cube. Similarly, then if we try to find out the coordination number, so each atom is coordinating with how many adjacent atom, that is what your coordination number means, right? So if I take this particular atom, so this blue atom, so that will be coordinating with the adjacent atom immediately, because there is a connection. So immediately here also one more atom will be there, 1, 2, and there will be another connection here, 3. Okay. Similarly, so this is, let us say, this is your positive x. Okay. So this is negative x. This is a simple x and y coordinates, right? So in this atom, this is a negative one, and similarly here also one more atom will be there. This is in the y direction, positive y. Okay, if I take it in this particular direction, and similarly if I expand it, one more atom will be there. Similarly, if I expand it, one more atom will be present. So how many atoms are there? This atom is being coordinating with 1, 2, 3, 4, 5, 6. So the coordination number will become 6. Right. So if I tabulate entire information, okay, I'll erase it and let me erase it, everything. So if I erase it, so you look at the details, what is coming. So if I tabulate all information, the relationship between the lattice constant and the radius, we have found out that A that is equal to 2r. Then the effective number of atoms we have calculated it to 1 atom, right? And then the atomic packing factor is coming at 0.52 and coordination number is 6. So this is how we will be finding out all the parameters for a particular crystal structure. So this is for simple cubic structure. So similarly, we can also find out for the face centered crystal structure and body centered crystal structure. So that we will see it in the next class. So in summary, if I recall, so we have discussed the total crystal structures that can be present for the metals, that is 4 crystal structures that we have discussed. One is a simple cube, then we have discussed FCC, BCC and HCP. Then we have discussed in each and every case how the atoms are arranged in the crystal structures in the metals that we have discussed, and the 2 important characteristics, one is APF and coordination numbers, Cn, we have defined it and we have seen the calculation for simple cubic structure, right, and those numbers are 0.52 and 6. In the next video lecture, we will calculate the APF and coordination numbers for the FCC and BCC structures.